So again, in this video I'm going to start defining parts of the curve using equations, and the first thing I want to start off with um, is the arc length, right? The arc length. You can it's denoted A, L, or S. Arc length is denoted A, L, or S. Most of the time you'll see L. Most of the time you'll see L. So the length is usually L. But there's a generic formula for arc giving, subtended by a certain angle. And now what is that? That's S is equal to theta R. Right? S is equal to theta R. Where S is the arc length, theta is the angle subtended by that certain amount of arc, and R is your radius. And this theta is in where theta is in radians. And there's pi to get from radians to degrees. There's pi radians, pi rad in 180 degrees, right? Pi radians is equal to 180 degrees. I shouldn't do divided by. Pi radians is equal to 180 degrees. Okay, so let me put this in surveying terms. L, which is S, L is equal to theta, or delta. Theta is going to be now delta, our angle subtended by the arc, delta times, it's going to be 180 over pi times R, right? Because we want theta's in radians for this. We want degrees, so this will give us degrees. Radians will cancel and we'll get degrees. So that's the definition for the length of a curve. Alright, now let's define the chord. The chord, which is this distance here. This whole distance. Oops. Chord is this whole distance here. But to solve for the for the chord, I usually draw, which is probably, it's probably good to draw, is divide the delta by 2, right? So you get exactly half the curve, half the chord. This distance would be the chord over 2. And this is going to be delta over 2. This is going to be delta over 2. Right? Because, there's no other real way to solve for the chord. This is the easiest way to solve for the chord, is break this up. We have a right triangle, and we have to use a little trigonometry here. So what do we have? We want to solve for the opposite, right? We want to solve for the opposite given the radius. So we're going to say that the sine, so let me circle, this one's done, L is done, we define that. Now we're going to work on the chord. So the sine of delta over 2, right, is equal to opposite the chord over 2 over the radius. Right, so now we want to solve for the chord. So the chord, the 2 and the R are on the bottom, and the radius are on the bottom. So, I'll just move this over. R, which means R sine delta over 2 is equal to c over 2, which means c is equal to 2r sine of delta over 2. That's the definition of the chord. Definition of the chord. Alright, now to get the tangent, solve for the tangent. Remember, the tangent is this distance up here. Alright, that distance up here. So how can we solve for that? Right, how can we solve for that? Well, it's going to be, right, tangent is going to be opposite, right, opposite over adjacent. It's going to use the R, because this angle is 90 degrees in here, right, because it's, whoops. Right, this angle in here is 90 degrees. I don't know why I keep doing that. Right, and here's, that's 90 degrees because it's tangent at that point. That's the point of tangency. Right, the point of tangency, or the point of curvature, depending on where the stationing is. Right, where the stationing is along this road. Right, there's usually, I don't know if I mentioned this, but the horizontal curves are usually used for road designs. Right, so, okay. So, the tangent, the function, the trig function tangent of delta over 2 is equal to the opposite, is equal to the tangent t over r. Right, so this is an easy one, which means t is equal to r tan of delta over 2. Right, that's the definition of the tangent. Alright, so what do we have left? We have our external, and we have our mid-ordinate. Our external is here to here, right? That's E external. So how can we solve for that? How can we solve for that? Well, we can see that this whole side we'll call Z. Let's call Z, the whole side Z. This whole length from here, the point of curvature, to the point, curve center, the curve center to the point of intersection is equal to the distance Z, right? And what is that? That's R plus E. Right, so that whole distance is equal to R plus E. We can use the cosine, right? The cosine, given the radius, right? We'll use the radius and this whole distance Z. So the cosine of delta over 2 is equal to the radius R, cosine adjacent, over Z, the whole distance Z. But what is Z? We said that Z was R plus E, so the cosine of delta over 2 is equal to R over R plus E, right? Which means that R plus E cosine of delta over 2 is equal to R. So move the cosine over to the other side, which means R plus E is equal to R over the cosine of delta over 2. So now if we minus R from both sides, which means which means E is equal to r over the cosine of delta over 2 minus r, or which is equal to r 1 over the cosine of delta over 2, whoops, not that, cosine of delta over 2 minus 1, right? Which is equal to, this is the same thing as equal to r times the secant of delta over 2 minus 1. Right? This is usually used though. This one's usually used. The external is equal to r times the 1 over the cosine minus 1. 1 over the cosine of delta over 2 minus 1. So that's how you derive the external. The mid-ordinate. The mid-ordinate. Well, this, let's define this short distance here as x. Right? This distance from the C, the chord, to the curve center as x. Right? So then r is equal to x plus m. Right? We defined, I didn't draw it in there. We defined this distance here as m. Oops. Right, this is m in here. The distance between the curve, the arc, the length of the curve, and the chord directly in the middle, right, where the chord is directly in half. You know, that's the mid-ordinate. So we said that r is equal to x plus m. So if we solve for x, what's x? Using x and r, we'll say that the cosine of delta over 2 is equal to x over r, right? So x is equal to r cosine of delta over 2. So if we plug this in, for x, right, let's do that. So r scroll down a little bit. R is equal to r cosine of delta over 2 plus m. So if we minus this, m is equal to r minus r cosine of delta over 2. So m is equal to r times 1 minus the cosine of delta over 2. And there we have it. Using trigonometry, we have solved for each part of the curve. Right? We solve for each part of the horizontal curve. These horizontal curves are usually in, developing subdivisions or highways or, any sort of thing. Surveyors need to know each part of the curve to do this kind of design or to retrace previous surveys. In the next video, I'll do some examples of using these equations for horizontal curves. See you soon.